Yeah, so now how can we use this Höfting bound? Well, the Höfting bound tells us how many instances we should look at, and that's it actually. So the first proposal here to use it is the so-called very fast Höfting tree, or the very fast Höfting trees. It optimizes the Höfting tree as follows. So if we have ties, so x1 and x2 have a g value which is very similar, or even more than two attributes have very similar g values. Potentially many examples have to be seen or looked at in order to make a stable decision with a high confidence. So obviously, if x1 and x2 are very similar, then delta g prime is very small, and so on and so on. So in that case, it's obviously wasteful, as it probably makes not a big difference which feature to choose. So in that case, the very fast Höfting tree breaks the ties by splitting on the current best if the current delta g is smaller than epsilon, but also smaller than tau, where tau is a user specified threshold. Yeah. And also, to make it a little bit more faster, the G computation is speeded up by the following idea. I mean, it's inefficient to recompute G for every new sample which is approaching, because it's quite unlikely that the split decision will be made at that specific point. So this variant, the very fast Höfting tree, allows the user to specify a minimum number of examples that must be seen at one node before G is recomputed. Yeah. So yeah, that's it. And this may implement a smaller delta, yeah, because we probably break the delta boundary before G is recomputed, but we don't care, because it yields a speed up, and it just, I mean, we do the same decision anyway, so to say, yeah, but faster actually, and with a higher confidence even. Yeah, the limitation of the Höfting trees is that, the Höfting tree or Höfting trees accommodate new instances from the stream, yeah, but it does not delete anything, so it doesn't forget. And the problem is that, the tree grows with time, because only at the leaf nodes we can split the tree. Yeah, so at first the root of the tree is split, yeah, and then after another set of samples, enough samples came in so that the Höfting tree, the Höfting bound can be used. We split a leaf node, so the tree grows, but it grows from the leaves. Yeah, so you see here the tree grows and grows and grows. So the tree may become extremely complex over the time, and you probably know from the decision tree chapter from KDD1 that decision trees tend to overfit, especially if they are very complex. So this is a very severe problem, and also the historical data dominates the decisions, because historical data has been used to find the splits at the highest level. So the split at the root node has been determined by seeing the very first observations from the stream, yeah? And they are there forever, so the root is never changing. So the first nodes, if the decision is done at a very early stage of the stream, it is not changed anymore. Yeah, so only at the leaf level, the most recent objects have been used to do the decisions. Yeah. To do the splits. So historical data dominates obviously decisions, because the very first decisions are based on this historical data. So adapting to changes is extremely difficult for these basic Höfting trees here. Yeah, and in order to overcome that, there are a lot of variants to the basic Höfting trees proposed in the literature. So, for example, the adaptive size Höfting tree introduces a maximum size, so then a maximum number of splitting nodes. So when this threshold here is reached, the tree is completely reset, and everything is done new from scratch. Yeah. So test for the limit after each node split, and if the limit is reached, then the tree is completely resetted. Yeah, but the problem is, due to the reset, the tree forgets everything, yeah, and loses also all information learned so far. Yeah, so you see it here, the tree grows, and at some point in time the maximum tree size or maximum number of nodes is reached, and then the whole thing is thrown into the trash bin, and we start off from scratch with the next instances, and then splitting the node again, the root again. Yeah, so obviously at that point in time we forget everything we have learned so far, even the most recent things, yeah, which is quite hard probably. And then we have the so-called concept adapting Höfting tree, which is another variant. So that starts to maintain, or the authors here propose to start maintaining an alternate subtree, not an alternate reality of fake news, but an alternate subtree when the performance of a node somehow gets worse. Yeah. So and yeah, when the new subtree starts performing better, it should replace the original one. And if the original subtree keeps performing better, then the alternate subtree is deleted again. Yeah. So and the original one is kept. So you see it here. We start off as before, and at some point in time here, we see that this branch seems to somehow deteriorate performance-wise. So we start maintaining an alternative subtree. Same here, and the same here in the root node. And at some point in time, you see that this alternate branch here does not yield really better results, so you delete it. And in this case here, you keep the new one and delete the original ones, and so on and so on. Yeah, so it obviously allows you to adapt a little bit better to concept drifts. Yeah, and then finally we have the so-called ensemble, so the adaptive size Höfting tree ensemble. So it uses adaptive size Höfting trees, but instead of using only a single tree, we use a combination of k models to increase the accuracy, and we combine a series of k learned models in order to get an improved consensus model, which is the classical idea of an ensemble. Yeah, and to predict the class of previously unseen records, we aggregate the predictions of the ensembles. And there are different combination methods, as you may recall from ensembles. So we have bagging, boosting, and stacking. So here, typically, we use for the Höfting tree ensembles, people typically use bagging. So you use bootstrap aggregation to generate small training samples, and then learn one model for each sample. Yeah, training subset, so to say. Yeah. So the bagging uses different sizes of training set. So you have smaller trees which adapt more quickly to changes, but you also have larger trees that perform better during periods with no or little changes. Yeah, so you have an ensemble of several trees. Each tree have a different height. Yeah, so a different size, and the smaller trees are more adaptive. The larger trees are more somehow conservative if nothing changes. Yeah, yeah, and you use a maximally allowed size for the nth tree, a threshold for that, which is typically twice as the maximally allowed size for the n minus first tree, and each tree has a weight proportional to the inverse of the squared error it gets, or it produces on the training set. Yeah, and the goal is to increase obviously bagging performance by tree diversity. So the classical idea also from random forests, we know from random forests already. So here is a visualization. You see here that you have trees at first that have quite similar height, but then it diversifies somehow. And at some point in time, for example, this one here, is it a blue one? Say it's the blue one. That is too high now, and now it is resetted. So at the next time slot, it starts from scratch. Yeah, and the same holds true for the yellow one, one step earlier, and the same holds true for the gray one here at this time slot and here at that time slot. Yeah, so yeah, you just keep different trees with different height and different number of nodes, actually, different number of splits. And if it gets too large, one of the trees gets too large, it is just resetted. So that is the same idea of the adaptive size Höfting trees, but now you just maintain an ensemble of those trees. Yeah, and that's it for the Höfting tree family. So just an overview. All of those trees, so ADA should be this concept adaptive. Yeah, it should be KHUT. But anyway, so with ADA, with this acronym, we mean the concept adaptive Höfting trees. All of those trees accommodate new instances from the stream. The basic Höfting trees, do not forget adaptive size Höfting trees. Forget by resetting the tree at once, yeah, completely once its size reaches a given limit. The adaptive concept Höfting trees, forget by replacing subtrees with new ones. And then we have these ensembles, typically the bagging adaptive size Höfting trees, for example, that uses varying size trees to respond differently to changes. So the smaller ones are more adaptive, the larger ones are less adaptive and more conservative in that case. Yeah, that's it for the decision trees for streams.